Right, so if these are sentences of the language, P and Q, then our syntax rules for L tells us that their conjunction is also a sentence. So, and again, I didn't introduce specific rules for parentheses in forming sentences, but the intuition here is that whenever you have a parenthesis, whatever is inside that parenthesis is supposed to be a sentence, or you are suggesting that it is a sentence. So it's just a means of grouping together stuff in order to be more, to have more clarity. It's supposed to be intuitive, but you pick it up as, the longer you work on this, the easier it is to pick it up, just like any symbolic notation. So, and we know that if P is a sentence of L, or a well-formed formula of L, and Q is a sentence of L, then P or Q is a sentence of L. We also know that if P is a sentence of L and Q is a sentence of L, then by the rules of the syntax, then P implies Q, or if P then Q, which is the same thing, is a sentence of L. We also know that if P is a sentence of L, then not P is a sentence of L. And we also know that if P and Q are sentences of L, then P if Q, so P if and only if is a sentence of L. Right, so any questions here? And this, again, these are syntactic rules for L, so the grammar. These are not deductions, okay? So let me just try and give you an example with English. This might clarify some stuff. So for example, so suppose you have a sentence like, so I could, from this, I could just put together the following sentences. Let's just call this cat Tom, just to give it a name. So for example, if these are sentences of English, so the question, so I guess the first question I want to ask you is, why are these sentences of English? Intuitively, just like give me an intuition.
Verbs and adjectives.
Right. I mean, yeah, I guess what part of what you could say is here is that when you're talking about verbs, adjectives, subjects of sentences, etc., all of those things are part of the grammar of English, right? So when you are learning how to, use passive voice, active voice, and all that stuff, I'm not a native English speaker, so I had to learn English grammar when I was, 9, 10, and it was really weird, really confusing, because it's very different from the Spanish grammar. But and obviously, native English speakers like yourselves, the way in which you learn a lot of English, most people learn English is just by talking with their parents when they are kids. And then obviously they go to school and they still have to learn grammar, but they already have like some sort of mastery of the language. But it's always more difficult when you are not a native speaker and you have to both master the grammar and then try to use it at the same time in combinations. But intuitively, the idea here is that in order for something to count as a sentence of English, it has to be like some sequence of symbols that go together according to the rules of English, for example, right? So we know, for example, that For example, this has English words, but it's not a sentence of English. So this is not a sentence of English. It doesn't matter that it has English words. In order for it to count as a sentence of the language, it has to fulfill the minimal requirements to be grammatical. And this is just not grammatical. It does not satisfy proper grammar. So, and I can put together, a bunch of nonsense, weirdo expressions that have English words but don't mean anything at all. So, so that doesn't mean anything either. It's just a combination of symbols that has no meaning at all. I mean, the words are words of English, but a sentence is, is a structure built up out of words. It has more, it has words as parts, but in order for something to be a sentence, it doesn't suffice that it has words as parts. It must have the words as parts in a proper way, right? And what do we mean by proper way? Well, according to the grammar of English, right? So these last two are not sentences of English, but the two above are sentences of English. The cat Tom is white. And the one below, Moises is a teacher. There's an object, they attribute something to the object. So in this case, the cat, and they attribute an adjective to the object, and so on with Moises. So it satisfies the proper grammar of English. And then you have to think of this syntax for L rules as analogous. It's just the idea that the idea here is that for L, we are not interested. The only thing that we're using L for, the artificial language L for logic, is to represent logical relations. It's just a model. It's just a representation. It's like a toy model of a language, written down schematically in variable form. And there, again, as I emphasized in the other lecture, the reason to do that, to just simplify language so much, is because when we are working and trying to figure out the complex properties of an object, a typical way of doing so, the scientific way of doing so, is just by creating a model of the object that abstracts away any details which are irrelevant. So because all we want to study from language, right? In this course, in this course, or for the purposes of logic, the only thing we care about are the logical relations between sentences. We don't care about specific meanings. We don't care about active and passive voice. We don't care. Those things are irrelevant to us, right? So just as, for example, when you're thinking about arithmetic, for example, suppose that that someone was trying to always use arithmetic by thinking about the specific objects. For example, like 2 candy bars and $3 and 5 airplanes. And they didn't have, for example, they couldn't use just numerals like that. They just couldn't use 2, or they couldn't use 3, or they couldn't use 5 as general ideas, as general concepts. It obviously will be very difficult to think of, putting together stuff or using addition. Or imagine, for example, that you didn't have the concept of a thing, so this concept here, thing, right? So this is like a really useful concept, right? I mean, because it can refer to anything at all. It's like an informal, so informally, this is like, in logic, the idea of a thing is just what I have been calling an object. It's just an expression that serves to just refer to any particular entity. But imagine that we didn't have that level of abstraction. We couldn't really talk about those things, right? So abstraction is a friend of reason and rationality and of pragmatism as well. Pragmatism and reason are divorced at all. There's feedback. There's mutual feedback between them. Reason helps us get things done. So, and one way of getting things done is just to, for example, if you have a problem, is always break it down into its simpler parts, try to simplify, abstract away from irrelevant details, etc., etc. So those are solutions that work in general for any problem, not just in logic, right? So the reason why we are doing this in logic, talk about some abstract language L, is because we don't care about the logic of English or the logic of German or the logic of Spanish. They don't have different logics. They all have the same logic. Logic works the same in all of those languages. As I mentioned the other day in my lecture, logic is really not about the mind, or it's not about the language. It's not about language. It's about certain structures out there in the world, you know, certain computational structures. So part of what we want to do is, because we use language to represent the world and to talk about the world, and we reason using language, then it is important to abstract away from the irrelevant details of language and use an abstract model of language, the language L, to see what are the features of languages in general and see what are the logical properties of language. So that's what the rules, the syntax for L rules are like. And again, we're not, the main point of introducing that was not so much that we're going to be doing a lot of exercises translating from English to the language L. We are not going to be doing that. But it is important that you at least grasp the essence of why we have to specify these rules for the language L. I could have just given you the rules for inference. You know, if you have premises of this form, then conclude this. But that's just a less rigorous way of doing so, of doing things. It is important to appreciate the sort of structure that we're dealing with. So these syntactic rules are just rules for putting together stuff, right? And then, for example, to continue with the analogy, if I know that the cat named Tom is white, is a sentence of English, and I know that Moises is a teacher is a sentence of English, then I know that this is a sentence of English. And indeed, this is something that all grammars have in common. Like the logical part of every grammar has this in common, that every grammar of every language respects the logical properties in this respect. And I mean, there's like a super interesting question there involving anthropology and empirical research of how languages behave, etc. And you know, the nature of linguistics. But you know, it will just take us too far from the current discussion. But for example, the work of, you know, UMass actually has one of the best linguistics department in the world. I don't know if any of you knew that. Like undergraduates usually are not aware of the ranking of the graduate departments. For example, the philosophy department for UMass is actually pretty good, in the you know, pretty well ranked. It's, you know, it produces very good research, right? I mean, you know, don't get me wrong, rankings are just a tool. I'm not saying that rankings are like everything there is or anything like that. They're just a metric, but they can be useful. And UMass has a really nice linguistics department. So, but anyway, big parenthesis. The point is that there are these logical structures common to all grammars. So if you know that P is a sentence of a language and Q is another sentence of that language, then their conjunction is also going to be a sentence of the language. And so on for these other sentences. So for example, if this, I could say something like, if Moises is a teacher, then the cat named Tom is white. That's also a sentence of English. But just notice how implausible it is that, so I mean, and this is just another way of showing you how this these rules for grammar have nothing to do with rules for deduction. They are just not the same thing at all. So suppose that you have as a premise, Moises is a teacher. And then you have as a conclusion, therefore, if Moises is a teacher, then the cat named Tom is white. I mean, without doing any detailed analysis of this argument, it just looks highly implausible that that conclusion follows from that premise. Or for example, you know, or even something like this, right? So for example, therefore, Moises is a teacher if and only if the cat named Tom is white. So this is another argument. Just let me put it clearly here, just in case someone might get confused that I'm saying that this follows. So, and I mean, the point of all this is just to be super clear that the fact that if you have two sentences, P and Q, and that you can put them together in a way that if they were sentences of some language, they, you know what, and you put them together, that's still a sentence of the language. That's very different from the fact that if you have these two sentences, then that thing that is also a sentence is going to follow logically. It has nothing to do with each other, right? So this is super important. Okay, so does anyone have a question about that? Or anything that I have just mentioned? Any clarificatory question, anything like that? So does the analogy with English help understand what's going on with the syntax? But notice also something interesting, because people think that, I mean, this is obviously like the end of some people thought that this was like the end of the road here for the syntax. So for example, you can, what do I mean by the end of the road? I mean that if you have a sentence P and a sentence Q, then according to the language L, you can just put together this, you know, you can just like go up above one level, right? So from P and Q, you can get this, from the sentence P and the sentence Q, you can get the sentence P and Q, and the sentence P or Q, etc. But obviously you can, I mean, this is what is called a recursive procedure. So what that means is that this is a procedure that can go on indefinitely. So it can go on indefinitely. There's always a successor. So for example, if P and Q is a sentence of L, then P and Q, and so for example, if P and Q is a sentence of L and R is a sentence of L, then P and Q or R is a sentence of L. Or if P and Q, then R is a sentence of L. Or P and Q if and only if R is a sentence of L. You see what I'm saying? So let me just. So suppose I have just determined that this is a sentence of L. because P and Q are sentences of L, I know that this is a sentence of L, right? So according to our rules. So this means that this thing here all of it inside parentheses because it's just another expression. And it also means that, so sorry, let me. So you see what I'm saying? You can keep iterating this procedure indefinitely. Once you find out that some things are sentences of a language, you can just keep putting them together and form larger sentences. And indeed, that's what happens in every language. So for example, how is it the case? I mean, and this is something which is, again, something from linguistics, but which is super interesting. How is it the case that human beings that are finite beings, how is it the case that we can never run out of things to say? How is it the case that we can always put together new sentences, new forms of expression? And part of the idea is because language also has this property. Like every natural language, I don't just mean the language of logic, which is the recursive property, so that I can take any two expressions of any language and then just put them together to form a new expression. And obviously there's no limit to this procedure, so that I could put, I mean, the only thing that's stopping me from putting together an infinite sentence is the fact that I'm going to live a finite number of years. There's actually an interesting paradox related to that, which is called the Tristram-Shandy paradox. Might mention it in a little while in a couple of lectures. But yeah, that both the grammar of natural languages and the syntax of L is such that you can keep adding on sentences. So is that clear? Do people understand what I'm saying here?
Yeah, I understand, but is it true that like this number is infinite, or is it just very, very, very large and kind of out of our capacity?
Yeah, no, that's an excellent question. So the point, I mean, strictly speaking, you're right that it's only potentially infinite. So it would be false to say that it's really, really large, because if I say that it's a really, really large number n, so for example, suppose that I say there's only going to be a really, really large number n of expressions I can put together, right? That will, I mean, there's nothing preventing me from putting together an there's nothing in the logic of language or in the logic of any grammar that prevents the universe from putting together an expression of n+1 sentences. So it's just that the point that I just mentioned right now, that we don't have, human beings live a finite life. We live a finite number of years. So saying that it's a specific number n will be false, but it will be more accurate to say that it's a potentially infinite number, so that for any number n that you can think of, for any number n of sentences, you could put together an expression having those sentences as parts, right? That's right. A true statement. Okay. Mm-hmm. And I mean, interestingly, some of these things that I'm just mentioning, or some of the, or many of these things have to do with, the higher reaches of more advanced parts of mathematical logic, or the logic of what is called computability, etc., etc. Also, the properties of the natural numbers, because if you notice, there's like the stuff that I'm just talking about, and that's related to the lecture of last Friday. It has to do with a very specific structure, the structure of the natural numbers, the ones that satisfy the piano axioms. So if you notice, they have the sentences in the language L actually have exactly the structure of the natural numbers. We start out with a base case, just as the number series are base case in arithmetic. And then we have successor expressions. And then we can build up more and more complicated expressions. So for any expression, you can always find a successor. There's always going to be a successor expression. So yeah, and those are results that can actually be demonstrated. So yeah, but that's, again, that's something super interesting that unfortunately we cannot really go deep into. But anyway, so having said that, let me quickly start out. We're not going to be able to cover much ground here right now, but let me quickly go back to this. So again, something that we have emphasized a lot of times is that not any expression of a language can count as a sentence, even if it's grammatically correct. Some of them may be questions, some of them may be orders. So in order for something to be a proposition, it has to be a meaningful claim about the world, right? So for example, the examples that they have here, roses are beautiful, that's a proposition. Did you like the movie? That's a question. It doesn't count as a proposition. And then part of what he does, or what he or she does here very quickly, this person that is the author of this handout, part of what they do is they give what is called the truth tables for the basic logical connectives. So, for example, conjunction usually in symbolic logic is represented by this symbol here. You're not going to have to learn how the symbolisms, but that's usually how people summarize it. Like this. This is how and is represented. And then this is how the values are computed. So for example, suppose that you have a statement of the form P and Q, and you want to know what's the truth value of that statement, right? Then in order to determine the truth value of a compound statement, and again, what I mean by a compound statement or molecular statement has to do with whether the statement has logical connectives inside it or not, right? So, and what are the logical connectives? And, or, if and only if, not, if then, or implies. And obviously, we have the quantifiers, which are sort of, logical as well, but right now we're just focused on what I call the propositional fragment of logic, the propositional part. So notice that the truth table for conjunction basically tells us for any truth. So we're obviously going to be only considering two truth values, truth and falsity. Sometimes they are represented by ones and zeros as well. So notice that the truth table for conjunction tells us that for any assignment of truth values to P and Q, there's a unique assignment that corresponds to their conjunction. So if both P and Q are true, then their conjunction is going to turn out to be true as well. And in every other case, their conjunction is going to turn out to be false. This is supposed to be sort of intuitive. So for example, if I tell you that I am a teacher and the moon is made of cheese, you might say, that's something weird that to say maybe in a conversation, but perhaps I could say something like, I am a teacher and today is Monday. And some of you might be, weirded out by that and tell me, no, it's Friday or something like that. And part of the idea is that whenever I put forward a conjunction, I'm making I am claiming that those two things are true. So obviously it's only going to turn out to be true if both are actually true, and it's going to turn out false in any other case. So that's the truth table for conjunction, okay? And here are some examples. You know, the capital of Ireland is Dublin, and penguins live in Antarctica. This conjunction is true because both of the individual propositions are true. A square is quadrilateral and fish are reptiles. This conjunction is false because the second proposition, fish are reptiles, is false. So that's the truth table for conjunction. I think it's very intuitive. I mean, I should be uploading this to the course folder, to the course readings folder. And this is, and again, this is going to be when we finally move on to induction. One thing that is going to be interesting is that, for example, in logic, we are only dealing with two truth values, 0 and 1, or truth and falsity. But part of what, you know, part of what reasoning with uncertainty does, as when you're reasoning with probabilities, is that you take seriously the idea that you could give a credence to a proposition that is less than 1 or 0. So like how plausible something seems to you, for example, right? It might not seem fully certain. It might not seem fully uncertain. It might be something in between. But in the cases of logic, we are only dealing with two possibilities, right? Or either it's true or false. So the truth table for disjunction, again, you have P and Q. We take them as, we are going to be taking P and Q as atomic statements, or just statements that have no logical connectives inside them. And then their compound, P or Q, which, you know, the main connective there is obviously going to be OR, the logical connective OR. So if P and Q are both true, then their disjunction is going to be true. And it's actually, for disjunction, you get a sort of an inversion of conjunction. So all cases are true. For example, if just as long as one of the disjunctions is true, one of the disjuncts is true, sorry, the full disjunction is true. It's only going to turn out to be false if both are false. So for example, suppose I tell you something like, it's either Monday or Friday. That's going to turn out to be true just because it's Friday. It's a true disjunction. But even though we rarely, I mean, it's not so common that we use disjunctions where both disjuncts are true. We usually want to use a disjunction where one of the disjuncts is false in typical conversation. But sometimes we do use disjunctions where both disjuncts are true. For example, suppose that I ask you, do you want chocolate cake or key lemon pie? And you tell me I want both. Right. So I mean, there's nothing inaccurate about that. So it could be the case that, so suppose that someone tells you that you either have chocolate cake or key lemon pie as part of as your options, your alternatives. That's still perfectly consistent with you wanting both of them. So a disjunction is true just whenever one of the disjuncts is true. That's all it takes. Okay. But if both are false, then the disjunction is false. Okay. And that's always for every disjunction and every conjunction. The last one I just mentioned, right? And then again, something that that applied to our discussion of syntax, but also applies here. Once you have, for example, once you have a disjunction between two propositions P and Q, if you know the values of P or Q, you can compute the value of the disjunction. It doesn't matter how complex P and Q are. So for example, in this case, we have been assuming that P and Q have no, they are simple sentences like, Europe is a continent or something like that. But you could have, maybe P could be something like, if Europe is a continent, then Africa is a continent. Some compound statement like that could be P. Maybe P is representing that. The point is that if I know the value of P and I know the value of Q, no matter how complex they are, I can compute the value of their disjunction. Okay. So any questions about that? Any questions about conjunction and disjunction so far? The conditional is a little bit of a tricky case, so I'm going to leave it for the next video lecture that I'm going to be uploading. But I mean, I guess they don't cover negation here because it's too obvious. But obviously, what negation does is you take a proposition like P, and the only thing that negation does is it inverts the value. So if P is true, then not P is going to be false. If not P is true, then not P is going to be false. And not P is going to be equal to P, right? So we already covered that we have an inference rule in the list of principles of deductive logic that I gave you, which is called double negation. And what that rule tells you is that whenever you have a statement that has two negations, you know, it is not the case that P, that's exactly the same as saying P, okay? So P is true if and only if it is not the case that P, right? So that's sort of like, it works sort of like the minus sign in math. It just, so if P is true, then not P is false. If not P is false, then P is true, okay? And I guess, I mean, something that I guess I should, a sort of spoiler, I guess, is that part of what it means to talk about validity in an argument, or to say that a conclusion follows from the premises, is that an argument is this sort of compound of propositions. And when you compute the values of the premises, when you know, with this sort of truth tables devices, then if the argument is valid, it's going to turn out that that you're going to be able to, just using this sort of truth table devices, see that if the premises are true, then necessarily the conclusion must have the value true. That's part of what it means to say that an argument is logically valid. You know, as I have been mentioning, it has like many different equivalent definitions. And when I say equivalent, I don't mean that they are equivalent in the sense of meaning. I mean that they are describing the same phenomenon. But anyway, I think I'm running out of time, but I'd like to see if there are any questions before we leave. Or comments. Okay, well, then I guess I'll see you next Friday. And again, there will be an assignment covering last week and this week. Yeah, just email me any questions or whatever, and I'll try to get back to you soon. I've been a little bit busy.
Thank you.
Thank you.
Thank you.
Thanks.
Thank you.
Thank you.
Thank you.